Yes, we know it for quite a while. The visible light spectrum. Newton worked extensively on it to explain the whole phenomena and was quite successful till some extent. Yes, he cannot explain the whole phenomena because of the particle. He cannot get the wave-particle duality at last. But yet, he did an excellent work to pretty much define it. It was quite interesting also, as an invisible thing could cross thousands of kilometers from sun, and on the earth it gets scattered into 7 different colors on dispersed on seven different colors, and the different colors, and the spectrum consists of all of the colors or all of the things or all of the material that has color that which we can see. Yes, it consists of all of the color sRGB. Well, that's not the point I'm trying to make. I'm trying to make the thing that's some more important or more exciting than the previous one. That's the spectrum. That is how some parts of the spectrum get deleted or get vanished when a particular amount of light is passing through it. That is, if we pass the spectrum or the scattered light from a ionized gas, particularly hydrogen, some parts get deleted or vanished in the visible light spectrum. But why only particular parts? Let's see that. Hey viewers, myself Syed Mohammad Saif. Welcome to my channel Guidance Science. Yes, the atomic spectra. Emission or absorption spectra. It is very shocking to note that when you heard it first time. It yields the same result in any part of the universe, and the result is very weird. Weirder than how the light splits into 7 colors. Yes? But I have some question for you. Why only specific wavelengths? Secondly, why the inversion of the parts when you go to absorption from emission? Third, how did it help us? And fourth, how quantization affects that? And yes, you may comment down before watching this video. And in this video we will deal with whole concept of how it works. I will answer all the questions, but before discussing it into elaborated manner, let's go into flashback. Spectra of hydrogen atom, which consists of a continuous spectrum with only some particular wavelengths excluded. The wavelengths belongs to visible light spectra, yes, because we can only see the visible light. But it also contains some part of infrared radiation and maybe not fully discovered yet some parts of ultraviolet or higher wavelengths also. But why did it happen? That's what the question is in this video. That's because the hydrogen atom utilized the wavelength, the specific wavelength, to make the electron excite. That means the particular wavelength, the energy carried by a particular wavelength is required and is enough to crack up and to excite electron in the hydrogen atom. That wavelength are very particular, and that's what quantization can define it. And how quantization defined it, we will see later. But that's what we know till now, and that's how the books explain. But that's not the whole point why we study it. Yes, surely. But today's video will get it clear to some extent. Yes, not fully. But let's get started. One question should arise. Why it doesn't excite if we give it extra energy than required? Suppose, take it by an example. If the energy required is E1 and we give it the energy that is E1 plus E2. First it will utilize, yes, it can utilize the energy E1 to get excited. And but what about the remaining energy E2? Because there is no way by which we can make the energy E2 to dissipate or to utilize it in another way. If the energy is E2 is equal to the another amount of energy required to jump in the higher orbital, then there is nothing you can do to make it jump or utilize the particular amount of energy. So that's why only E1 will help and nothing else. And that's how we do that. As I had mentioned before, the wavelength of light which get absorbed by the hydrogen is the specific wavelength. the energy of that wavelength is exactly enough to make the electron excite. By meaning of excite is it can jump from one orbit in this case, because the orbital was not defined till then, to another orbital. It could be various number of combinations, like from first orbital to second orbital, second to third, third to fourth, and it can go back and forth. And that's how the emission spectra is defined. When it comes from it comes from a higher orbit to the lower orbit, it emits a particular wavelength, and that wavelength is how we can find out which particular wavelength is emitted. And due to the maximum number of combination or various combinations, different types of waves or different types of monochromatic light can be discovered and can be utilized to make the electron emit. But how that so? The orbits that are fixed by the Bohr's atomic model are very specific, and to jump into that specific orbital, it needed an exact amount of energy. That means if we lower the energy which it needed, it cannot jump or cannot excite. And if we give that excess amount of energy, first of all, it will excite, but it has no way to vanish or no way to utilize that extra amount of energy into any kind of particular use. And in that microscopic level, it cannot be propagated using heat, because light also propagates heat. And why? They don't know why the excess amount of energy does not propagate as heat. In order to make the electron jump, the photon acts as an energy carrier. In the microscopic level, there is nothing other than photons to carry out energy, or electron or proton, because that is microscopic level, and how many times I will mention that I don't know. So by means of carrying the particular amount of energy, the energy which is exactly needed is transferred, and the excess energy which does not plays any role in the spectrum is faded away. That means it comes back without any increment or decrement. But that's one question which is in our mind exactly. Then what makes it to dissolve the whole wavelength, and what calibrates the whole phenomena? By which I mean that if it is going into a number of combinations, if the combinations are infinite and it can move from one orbital to another orbital, then there is small amount of group which utilizes from one combination of wavelength and some from another. But all the electrons cannot use the whole energy, or in our case the whole set of wavelengths or the whole set of jumping, and how the whole spectrum is dissolved in that. By that I means the whole energy cannot be resolved and cannot be utilized. So why the remaining amount of energy cannot show up in our spectrum, or in our case emission spectrum? But that's not known till today, because that's a very complex phenomena and the microscopic level cannot define. And yes, the particle wave phenomena is also very complex as compared to the macroscopic phenomena. But one thing is there which I can explain. It was by Swedish spectroscopist Jonas Rayberg. I think it's a familiar name. Comment me down if you know that. Which gave the equation wave number equal to 109,677 in bracket 1 by n1 whole square minus 1 by n2 whole square bracket close. That defined the combination, the particular combination, and wave number is nothing but the reciprocal of wavelength. So we can wavelength equal to n2 square minus n1 square divided by n1 into n2 whole square whole divided by 109,677. And by utilizing the wavelength, we can find out which particular wavelength is necessary to move the electron from one orbital to another orbital. That means if it's jumping from first orbit to third orbit, then we can use n1 equal to 1 and n2 equal to 3, and easily we can find out the wavelength which is required to move the electron. And that's how we define it. And it's important to note that there is only a particular sets of wavelength, so no other wavelength than that can calibrate or will be able to move that particular wavelength. And it is also defined that if we are giving it a particular wavelength or exact number of wavelength or exact wavelength which is required, then it will not accept the result from any other wavelength, because the extra amount of energy will not do anything. That wavelength will also resolve the whole. And if we see the number of orbitals or the wavelength required, as we move far away from the center, the distance between successive orbits will decrease, and so the difference between the wavelengths, the particular wavelengths or frequency, will also decrease. But why? As E equal to h nu, the energy difference between the two orbitals, that means the energy required by an electron to keep it into a particular orbital. Suppose that orbital is n1, and when it get excited into another orbital n2, the energy in n1 and the energy in n2, suppose is E1 and E2, then we can define delta E equal to h nu. So nu equal to delta E divided by h. So E2 minus E1 divided by h can give us the exact frequency which we have defined. So we can define it using the Rooiberg's equation, as we had discussed it earlier, and also by the idea of quantization, and that's how it works. Since the orbitals are uniquely defined, the wavelength could be uniquely defined, and yes, that's how we do that. I am Saif, meet you in the next one.